Good morning, good afternoon, and good evening, everyone, and welcome to the fourth session of the Scientist.com AI Innovation Series. My name is Chris Peterson. I'm the co-founder and CTO here at Scientist.com. And today we're going to focus on the transformer in its entirety, the overall architecture, and how it generates text. So this is part 4 of how large language models work. This is the last session of the how large language models work portion of the AI seminar series. It does go on, and I encourage you to attend because we have a lot of interesting topics coming up. But this is the last part of this section, and honestly, this is the talk that I really set out to give. This talks about the transformer architecture. The transformer is the T in GPT, generative pre-trained transformer. This is what actually generates the text. We talked a lot about the portions of the transformer, neural networks, embeddings, the attention mechanism, and this talk is going to clip right along because we've already talked about large chunks of it. So here's what we're going to talk about today. First, we're going to take a quick crash course in computer graphics programming. We're going to learn how computer graphics programmers use matrices and matrix multiplication to move vectors around on the screen. And we're going to do that because it's going to help us, or I hope it's going to help us visualize what's happening inside of the transformers. We're going to spend 3 to 5 minutes on what that looks like. Then we're going to talk about the transformer architecture. We're going to spend, honestly, the bulk of the time going through an example of training the transformer. Then we're going to use the transformer for inference. We have a couple other concepts to round it all out, and then we'll conclude. So first, how do we visualize matrix multiplication? So this is a graph, and we've seen graphs like this through this series. This is a 3x2 matrix with row-wise vectors, meaning it's got 3 vectors of 2 dimensions each. The first vector, A here, is 0, 1.5. The second vector, B, is 2, 1, and the third vector, C, is 1, 0. And we've seen visualizations like this throughout this series. To date, this is how we've thought of matrix multiplication, kind of numerically. This is the formula that we use to actually perform matrix multiplication. We've also seen how matrix multiplication can be used to compute the feed-forward step of a neural network. Today, we're going to look more at how you can visualize matrix multiplication. So what we're looking at here is our original matrix with 3 vectors multiplied by what's called a rotation matrix. And a rotation matrix is a subset of a type of matrix called a transformation matrix. Transformation matrix is actually where the transformer gets its name, which is why we're taking this brief little detour. So this rotational matrix, if I put the cosine of 45 degrees here and here, I put the sine of 45 degrees here and the negative sine of 45 degrees here, between the numbers you see here and the name rotation, you can probably already guess that when I do this multiplication, it rotates the vectors by 45 degrees. So you can kind of just see the vectors all move by 45 degrees. And rotation is not the only thing you can do with the transformation matrix. You can also scale. So here we have a scaling matrix, 2, 0, 0, 1. And if I multiply our original matrix by this new transformation matrix, what happens is it scales the x component of every vector 2x. So the x component of our second vector goes from 2 to 4. The x component of the c vector here goes from 1 to 2. And had I swapped these, had this been 1, 0, 0, 2, it would have scaled everything. It would have scaled the y dimension 2x and not the x dimension. And you can combine these. So if I take my rotational matrix here and I take my scaling matrix and I multiply one by the other, I end up with this matrix here. And if I multiply our original matrix by this new transformation matrix, what happens is it rotates, then it scales. Matrix multiplication is not commutative like scalar multiplication is. So if I were to swap these, if I were to move the scaling matrix to the front and multiply it by the rotational matrix, I would end up with a different matrix here, and that would correspond to scaling then rotating, which would give us a different set of vectors. Now, what I want you to take from this isn't necessarily how you make a rotational matrix or anything like that. It is that these square matrices, this is a 2x2 matrix because we're operating in 2 dimensions. These square matrices can be thought of as transforming the underlying vectors, as moving them in space, a combination of rotating around a dimension and scaling in all of the various dimensions. And it doesn't have to be 2 dimensions. We can scale this up to 3 dimensions. So what we're looking at over here is a little ball of vectors. This is something like 10 random vectors that I generated, all shooting out from the origin. And now we're in 3 dimensions. So our transformation matrix is 3 by 3. And what I've done here is I've set up a rotational matrix in the upper left, which means in the XY plane. If I'd wanted to do it in the XZ plane, I would have used different positions in this matrix, so the YZ plane would have been in different positions. And then I have a scaling matrix, also 3 by 3. So what this is going to do is it's going to rotate our object 360 degrees in the XY plane. It's going to stretch it 4x in the X plane, or in the x-axis, and it's going to compress the y-axis to 1/4, and it's going to leave the z-axis unchanged. And when I run that, you can kind of see that. It's a little bit hard to see with a big ball of vectors. So I did it again with a shape, and I changed the scaling matrix a little bit. But if I run this in 3 dimensions on a shape, you can see it much more clearly. It is stretching in a single dimension and rotating in a single plane. So that's the crash course. That's basically all we're going to talk about in terms of visualizing matrix multiplication. But what I want you to take is that these square matrices are moving vectors in space. It's a combination of rotating around different axes, scaling around different axes, and because they're square, they keep the vectors in the same dimension space. It is a series of, basically any matrix can be a series of rotations around different axes and scaling on different axes. Okay, so let that sort of percolate in the back of your brain, because we're going to come back to it as we move through the transformer. So what is a transformer? A transformer is a deep learning model that represents words as vectors and iteratively transforms these vectors by attending to contextual information to predict the most likely subsequent token in a sequence. Thank you, ChatGPT. It is a mouthful, but this is a very good definition of what it is, right? We've seen how words can be vectors. We are going to iteratively move these vectors through space using contextual information. That's all about the attention mechanism, which we talked about last time, all in service of predicting the most likely next token. In short, I like to think of a transformer as a way of traversing high dimensional meaning space. So this is in the embeddings talk and in the attention talk, we talked about how words can be embedded in these high dimensional meaning spaces such that the meaning of the word is retained. The transformer is moving through meaning space to find the next token. Okay, to see how that works, let's go through the architecture of the transformer. So this is the same image we showed last time. This is the canonical image of a transformer. It comes from the paper, Attention is All You Need, which again, I very much recommend everyone read. The first step is the embeddings. You can see here, there's 2 inputs. This is labeled outputs. We're going to come back to that in a second. But these arrows are coming into the transformer. The next step is positional encoding. This helps the transformer learn what position each token is in. We're going to talk more about that. The left side of the transformer is called the encoder. This whole chunk here is the encoder. And the right side is the decoder. Nice symmetry there. And then you remember this block from the last session. We called this the cross attention block. It is also referred to as the encoder decoder. So if you read the paper, you will see it referred to as that. There are 5, count them, 5 different add and norm step or add and normalize. We have 3 different attention blocks: self-attention, masked self-attention, and cross-attention. We talked about those last time. We have 2 feed-forward blocks. These are straight-up neural networks, the same type that we talked about in the first session. We'll talk about the architecture of those in a minute. And then we move on to the output probabilities. So you can hopefully already see that we've talked about a good chunk of the transformer already. So we're going to be able to move through this hopefully relatively quickly because there's a lot. Okay, so how do we train the transformer? Well, you will recall that to train any sort of machine learning model, we need an input and an expected output. So one of the things that this style of transformer is very good at is translation. So that's what we're going to do. So our input is going to be, where does the queen live? Stealing a sentence from our previous talks. And we're going to translate that into French. Où habite la reine? And now you will recall we have these sort of 2 inputs. This one's labeled outputs. I find that to be very confusing. I consider this to be the encoder input and this the decoder input, right? And the output is up here. We'll see why they call this output later. But for the time being, I'm going to call this the decoder input and the encoder input. And then this is our output. Okay, so we have 2 inputs. Our encoder input is going to be our input, our starting sentence here. Where does the queen live? And what we're going to do is we're going to tokenize it the same way we did in the embeddings talk, the same way, the same tokens we used in the attention seminar. And then we're going to prepend SOS and append EOS. These are special tokens. SOS is start of sequence. EOS is end of sequence. And this tells the sort of bookends the input. Then we're going to set up our decoder input, because 2 things have to go into the transformer, or this transformer, to give us an output. And our decoder input, for training purposes, is going to be our expected output shifted right. We moved everything to one position to the right, and we've prepended it with SOS. So you'll see that in the image. The outputs are shifted right. That means, OO is, instead of being the first token, is the second token, right? And we prepend start of sequence. We do not append EOS. We do not append end of sequence, because our expected output of the transformer is going to be Où habite la reine, EOS, end of sequence. So what the decoder is learning to do is, given this from the encoder, given where does the queen live, it's going to learn to translate or to move this input to be this input. And we're gonna go through that step by step. Or it's going to learn to move this input to be this output, pardon me. And we're going to go through that step by step. Okay, so this is the encoder. We're going to focus on that first. So hopefully this is kind of old hat by now, right? Hopefully you guys remember that if our input is SOS, where does the queen live, those tokens each become a row in our matrix. And using our embedding model, we end up with a vector for each, and the dimensions of our embedding model become the columns of our matrix. So this is how we generate the matrix, the same way we did in the attention talk. But what I want us to think of it as is a little ball of vectors, right? So we have 1, 2, 3, 4, 5, 6, 7 vectors here. So what we're really sending in is 7 arrows coming out of the origin. It's this little spiny ball of vectors. It's this little pincushion or sea urchin thing that you could hold in your hand. Now, it's not in 3 dimensions. It's in this case, 512 dimensions, but it is fundamentally this little ball of vectors. And this is what we're going to try to visualize as we go through. So the first step, once we've turned this into a matrix or into our ball of vectors, is positional encoding. Now, positional encoding is actually much simpler than it sort of sounds like. Positional encoding is essentially a matrix that you set up for the lifetime of the transformer. You're going to set up this positional encoding matrix, and you're going to build it using these two methods. In the paper, they talk about trying a couple of different methods, and they produced similar or nearly identical results. So I think there are other ways of doing this, but let's take a look at what this positional encoding matrix looks like. I added these as macros into Excel, and I generated a positional encoding matrix. And what you see here is the dimensions across the top and the positions along the side. So this would be position 1. This would be your first token, SOS. And this one here would be, where does each token would be in a different position. And what's happening is those methods, or these sort of functions, they generate this matrix. And this matrix adds a little tiny offset in every dimension for every position. But every position has a slightly different set of offsets. And what that means is you're taking every vector and you're moving it a little bit in space. You're just going to add this positional encoding vector to your input vector. And that's going to move those vectors in space just a little bit. But every position is going to move in a slightly different direction. And you can kind of see that in this pattern here, right? Every position has a different set of values. So every position is going to move in a slightly different direction. Why the heck would you do that? Well, ultimately, the matrix math that we're doing is not inherently ordered. And that might sound sort of funny, because just looking at it, you're like, well, every vector follows the previous vector. But in the math, it doesn't really work out that way, right? So if I take two vectors here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I multiply that by 1, 4, 7, 2, 5, 8, 3, 6, 9, I end up with a matrix here. If I transpose two rows, if I transpose two of these vectors, which would be the same as transposing two words in our input, and then I do the math out, I actually get the exact same values. It's just that the values are transposed, right? So the math isn't actually, like, there is no inherent order in the transformer. So what you're doing is, by adding these little offsets, slightly different offsets, different positions, if you were to add a positional encoding matrix to this, your output would end up being a little bit different. And that little bit of difference, the transformer can ultimately learn to distinguish between words that are in the first position, the second position, or the 150th position. Okay, so that's positional encoding. You've taken your ball of vectors and you've moved them just a little bit. Each position is moved in just a slightly different direction. Now we apply our first attention step. Now, we talked about this in great detail already, so I'm not going to go into the details of how attention is applied, but I do want to focus on the weights. We glossed over this intentionally in the last seminar, but you will recall, to apply attention, we need a Q matrix, a K matrix, and a V matrix. And to create those, for self-attention anyway, we copy our input matrix, our input set of vectors, and then we multiply them by weights. We multiply them by WQ to get the Q matrix, WK to get the K matrix, and WV to get the V matrix. WQ, WK, WV are all square matrices. In fact, we do this for every head of the attention mechanism, but we talked about that last time. The important part is that WQ, WK, and WV are all square matrices. These are transformation matrices. What these transformation matrices are fundamentally doing is they're taking that ball of vectors and they're rotating it. It's pushing and pulling and nudging and pinching and zooming and accentuating different parts of the meaning space to better apply attention. And the transformer, through training, is learning how to do that such that it can apply attention in a more meaningful way, such that it can extract more context out of this input. So then it applies the attention mechanism, then it multiplies it by WO, which is just one more transformation that the transformer can learn how to do. It's another transformation matrix. From there, you go into your first of 5 add and normalize steps. So every add and normalize step, you can see here, this is an image of it. It goes around, or it comes after one of these sublayers, either an attention block or a feed forward block. And for every one of them in the original image, you're going to see this little arrow here. This is called the residual. What happens is the input to that sublayer, either attention or feed forward network, you're going to copy it and you're going to send it around that layer. So the unmoved input is going to go into the add and normalize step, and then the output of the actual sublayer is going to go in. And you're going to add them and normalize them together. You can kind of think of this as not averaging, but you can kind of think of it as averaging. It's kind of backing off some of what the layer did, right? So it could be that attention had an extremely, like an extreme effect on the matrix. That's going to be a problem. It's going to make the transformer hard to train. So the add and normalize step smooths that out. It takes away some of the extreme changes, smooths it out, and it stabilizes training. Because if you moved it too much, you end up in what's called a vanishing gradient problem that we talked about momentarily in the first session. So this add and normalize step sort of smooths out the movements, stabilizes training, makes the whole network sort of easier to train. And we do this a lot. Okay, so now we've applied attention, we've smoothed that out a little bit. The result of that goes into a feed forward network. This feed forward network is exactly like the network that we talked about in the first session. It's just like the network that we use to train tic-tac-toe. Except this time we're going to send each individual vector through, which means that the input layer size has to be of D model, which is 512 in our case. In the transformer, the hidden layer is typically substantially bigger. It is typically 4x the D model. No reason it has to be, but that's what they found works. And then the output layer is also D model because you want your output matrix to be the same dimensions. So then you push your matrix through this feed forward network, which the transformer is learning. And this feed forward network is, again, moving all of these vectors through meaning space, or changing the meaning space around them is another way to think of it. And then you add and normalize again, sort of smooth it out, just smooth those changes out. Don't let anything be too extreme. And that's your encoder. You basically run through your encoder. Now you will notice there's this n times sort of nomenclature here. You actually run through the encoder 6 times. So the matrix that comes out of this final add and norm step, you're going to feed it right back into multi-head attention. You're going to do that 6 times. Every time through has its own set of weights. Right? It's going to keep sort of taking that ball of vectors and moving it a little bit each time. You're going to keep doing that and keep enriching the space, keep adding context to those vectors. And ultimately, after 6 is what they use in the paper, you're going to end up with your encoder matrix that comes out of it. And that's the encoder. You now move to the decoder, and you can just visually see the decoder. It has an extra step, but it's very, very similar. So let's go through the decoder. First step is exactly the same. You're going to use a different input. This time it's SOS, U Habit Lorraine, but you're going to create the matrix in exactly the same way. You're going to end up with another little ball of vectors, another little pincushion of vectors. You're going to apply positional encoding exactly the same way. Same matrix, same values. You're just going to move those vectors a little bit based on position. You're going to take that resulting matrix, you're going to pump it through another attention step. This is just like the first attention step, except that it's masked. So you're going to have a new WQ, a new WK, a new WV. You're going to move these vectors around, accentuate different parts of them, and run masked attention. And you will remember, in masked attention, we are masking, quote unquote, future words. We're going to talk about this towards the end of the training section. But you mask them by putting in a negative infinity above the diagonal. These positions correspond to words that are in the quote unquote future. And this is what's going to allow us to train the transformer very efficiently. These negative infinities, when you put it through softmax, end up at 0, which means we're allocating 0 attention to those positions, or to those words in each position of our matrix. We're going to come back to that. So we've applied masked attention. We've moved our vectors once in our decoder. Then we're going to add and normalize, smooth it all out, take out any extreme changes. Then we're going to apply cross attention. Again, same as the last 2 attention blocks, except this time K and V come from the encoder. So the encoder gets encoded or gets run one time, and then you can cache that output matrix. And every time you go through the decoder, you're going to use that same matrix for K and V. Q is going to come from our previous step. You've got a new set of weights, a new WQ, a new WK, a new WV. The transformer is going to learn how to apply attention here, which parts to accentuate to make it most effective. You're going to apply attention, and then you're going to smooth it out again. Add and normalize, just add and normalize, keep smoothing, stabilizing, training. The resulting matrix is going to go through yet another feed-forward network. This is your decoder feed-forward network. It's the same exact thing as on the encoder. Input layer of D model, hidden layer of 4x D model, output layer of D model, giving the decoder another chance to move these vectors, to learn how to move these vectors to a new place in meaning space. And then you're going to add and normalize again. Keep smoothing it out. Just every step of the way, you want to smooth this out. You don't want any extreme changes. And that's your decoder, right? Again, you've got this n times mark here, which means you're going to do the same thing. You're going to run it 6 times. There's no reason it couldn't be more or less, but in the paper they use 6. And the output matrix of this add and norm is going to go right back into masked multi-head attention. You can do that 6 times, and every time through has its own set of weights. It's learning more abstract concepts about the vectors going through. Now, the output of that is basically, the output of your decoder is going to be a matrix of the same dimensions as the input. So if we had 5 tokens, that would be a matrix with 5 rows. And if we had 512 embedding dimensions, that would be 512 columns. So in would come a matrix that's 5 by 512. Out would come a matrix that's 5 by 512. We don't want a vector out of our transformer. We want a word out of our transformer. That's what the linear step does. So we need to take this new point in meaning space, this vector that's been moved to a new place, and we need to convert it back into a word. And that's what the linear step does. So we go from a matrix that is 5 by 512, and we're going to multiply it out by a weight matrix. These weights are learned by the transformer. That's going to be demodeled by vocabulary size. And out of that, you're going to end up with a new matrix that is number of tokens by the size of your vocabulary. So if your vocabulary has 500,000 words, you're going to end up with a matrix that is 5 by 500,000. And the values in that matrix, you can think of them as kind of the distance that each word is from the point in meaning space that the original vector pointed to. Right? So you've got the output of the transformer is a bunch of vectors that are pointing to a point in meaning space. You're basically, for every position, you're figuring out how far every word in your vocabulary is from that vector. And that's what the linear step does. You then apply the softmax, which turns those, I'm thinking of them as distance, technically they're called logits, you're turning those values into a probability distribution, which then tells you how likely it is that each word in your vocabulary appears at each position. So what that looks like I'm showing what this would look like post-training. During training, it's going to look a lot more random. But post-training, what it's going to look like is if your decoder input is SOS, ou, habite, la reine, then your columns are every word in your vocabulary. You're going to end up with a probability distribution that says, from the token SOS, the next likely token is ou. Given SOS, ou, the most likely next token is habite. Given SOS, ou, habite, the most likely next token is la. And what we've done, these would be the post-training probabilities. During training, it's gonna be a lot more random. But what we've done is we're training the transformer to predict the next token at every position in a single pass, right? This is one of the innovations of the transformer is given this whole input, it's training, okay, if I'm given SOS and I'm given, where does the queen live? I know that this is the next position. The next token is this. Given SOS, ooh, this is the next token. You're training every position at once. And this is really where the masking comes in. Had we not masked, SOS would have had context for all of the next words, which it's not going to have during inference. You would have to train it for every position individually, which would make training exceptionally more expensive, especially for long sequences. So that is one of the things that makes the transformer so powerful is that masking allows you to train every position at once. Okay, so how do we actually train it? Because during training, like the first time you do this, it's going to be basically random. You're going to train it basically the same way we trained the neural net. The output of the transformer is going to be a series of probability distributions. So we have the actual output of the transformer. We have our expected output, ou, habite, la reine, EOS. You can use cross entropy loss, the same function that we used when training the tic-tac-toe neural network, to compute the difference, the loss between the actual output and the expected output. You can use the partial derivatives of that loss function to back propagate that error into the transformer. You can use the derivative of all of the functions in all of those layers to assign a portion of that error to every single parameter through your entire transformer. So this is much, much, much deeper than the neural network that we trained in the first session, but it is the algorithm is exactly the same. You're going to back propagate that error using the derivatives, and you're going to move all of those parameters in the opposite direction from that derivative. And that's how you're going to train your transformer to turn SOS, ou, habite, la reine into ou, habite, la reine, EOS. And that is training. So how do we use that? Now that we've trained our transformer, how do we use that to generate text? And that's called inference. So the setup for inference is very similar to the setup for training. This time we don't have an expected output, right? Because we want the transformer to give us the output, but we do have an input. Where does the queen live? We're going to set the encoder input up exactly the same way that we did. We're going to tokenize it. We're going to prepend SOS. We're going to append EOS. We end up with the same input. Since we don't have an expected output, that's basically just an empty array. You can prepend SOS to an empty array, and you basically just end up with SOS. So our decoder input is going to be a single token start of sequence. And then you're going to run through the encoder exactly like you did. In fact, because we're sending in the same values, you're going to get the same encoder matrix out. You're going to run through your multi-head attention, add norm, feed forward, add norm, do that 6 times, and you're going to get the output matrix that is your ball of vectors. Where does the queen live? All moved into a new meaning space that encapsulates all of that context. You're then going to run through the decoder. The only difference in inference than during training is that the decoder is run in what's called an auto-regressive mode. So the first time we run the decoder, we have a single vector. So that little ball of vectors isn't a ball of vectors, it's just one arrow coming out from the origin. We're going to run through all of the steps. We're going to go all the way through the decoder. We're going to do this 6 times. And out of the decoder is going to come one singular vector, but it's going to be pointing at a new point in space. And that point in space, the closest word to that point in space is going to be oo. And the linear step is going to make that clear, and the softmax is going to turn that into a probability distribution. And out of the other end of the transformer is going to come a single vector pointing to oo. Now the auto-regressive bit says, okay, if oo is the output, I want you to append that to whatever you put in. So we put in SOS, append oo. Now run the same thing, run that through the decoder. So now you're running 2 arrows through SOS oo. And you're going to run through all these steps, and every step is going to move those 2 vectors through space, through meaning space. And out the other end, you're going to end up with 2 vectors. The first one's going to point at oo. The second vector is going to point at habit. You only care about the second one because you already know the first token. So you're going to take habit, you're going to auto-regress that. Now you're going to have SOS oo habit. You're going to run that through, so on and so forth. And it's going to look something like this. So if your encoder input was SOS, where does the queen live, EOS, and your decoder input is SOS, that's going to move through space to the point oo. You're going to append oo to SOS, and both of those vectors are going to move through space to oo and habit. You're just going to take the last one, append it, so on and so forth. You're going to keep appending the last character and running it to your decoder input, and running the decoder until the last token to come out of the decoder is EOS. And that is going to be the trigger that tells the algorithm to stop auto-regressing. It's going to say, hey, you're at the end of the sequence, you're done, just stop. And what the decoder has fundamentally done is it has taken the vector that points to SOS, then the vector that points to oo, the vector that points to habit, la, and rain, and it's moved each one of those vectors slowly, iteratively, methodically through meaning space, so that SOS now points at oo now points at habit, habit now points at la points at rain, and rain points at EOS. And that is what the transformer is. That's what we're training the transformer to do with all of the back propagation. And that's it. We've now made it through training and inference. It's a lot of steps, but it's just moving those vectors iteratively through meaning space. There are a couple other concepts I feel like we need to talk about to really sort of understand it. The first one is temperature. So one of the things that makes ChatGPT and other GPTs feel so magical is this like element of randomness, right? When you ask it something, you get a different response, probably similar, but like different wording every time. But what we've just gone through is perfectly deterministic. Like everything that we just went through is perfectly deterministic. If you put the same input in, you're going to get the same output. That's because when we got to that output step, we had a probability distribution of words. So we knew of all the words in our vocabulary, we knew how likely each one of them was to be the next token. And what we did when we auto-regressed was we just took the most likely next token. That's called greedy search. If you do that, basically just, take the one with the highest value, your GPT will be perfectly deterministic. It will say the same thing given an input every time. That's not how most of them work. Most of them sample words out of that distribution. So they randomly pull words out of that distribution, but they pull them in accordance with the underlying distribution. So you're more likely to get a word that is more likely to be your next token. And that's where you get this element of randomness, and temperature is what governs how random it is. So a lower temperature means less random. A higher temperature means more random. If you put the temperature all the way at 0, you're back at greedy search, and you're just picking the most likely token. You're fully deterministic, and how high the temperature is varies per model. But that's how you get this sort of randomized output out of what is fundamentally a deterministic process. Very much related to temperature is something called beam search. So oftentimes when you're talking, the word that you choose to use is not necessarily a very likely next word. So when I think of a matrix as a little ball of vectors, and I describe that as a sea urchin or as a pincushion, those words are not very likely. They're not the likely next word. But as the analogy goes on, hopefully it comes together and the sequence of words makes sense. That's what beam search is trying to do. So with beam search, rather than selecting or sampling a single token out of the end of your transformer, you select a number of tokens, X tokens. Maybe it's 5, maybe it's 10. I'm not sure what the number is they use. And then you auto regress each one of those, and you select a sample output of each one of those, and you auto regress all of those options, and you do that to some depth. And then at various points, you're going to look back and you're going to assess how likely, based on the sum total of the likelihood of all of the probability distributions that came out of your transformer along the way, you're going to look at how likely each sequence of tokens is. And then you're going to pick more likely sequences of tokens. And this allows for more natural language, because sometimes language, you don't pick the most likely next word, but it comes together in the end. So that's beam search. Another way that GPTs sort of generate text that sounds very much like a human would generate. I also wanted to touch on number of parameters. So if you've been in the space and you've been following different models, you will have no doubt seen that they're referred to by parameter size. So Mistral is 7 billion parameters, and Nemo is 12 billion parameters. And I heard GPT-5 is going to be 1 trillion parameters. Don't quote me on that, but they're often referred to by the number of parameters that they have. These parameters refer to each of the basically numbers inside of the transformer that it has learned. So every WQ, WK, WV matrix, every value inside of that matrix is a parameter. You have one of those matrices per head, per attention block, per sublayer, per layer. That's a lot of different parameters. You've got WO, which is the matrix that you multiply the output of the attention block by. You've got weights for all of the feed-forward networks. All of the add and normalize, we didn't talk too much about this, but they have a scaling and a reshifting parameter. The embedding model's got parameters. The linear step at the end, where you transpose or you transform from embedding space to vocabulary space, those are all parameters. You basically add all of those parameters up, or you count all of those parameters, and that is the number of parameters in your model. I presume you just round to the nearest billion at that point. And that's how you get the number of parameters. And finally, the last thing that I wanted to touch on is we have talked about the transformer as it exists in the paper, Attention is All You Need. There are other forms of transformer. In fact, modern transformers are oftentimes decoder only. So they just get rid of the encoder entirely, and they just have a decoder. One of the nice things about doing this is you don't need a training pair of sentences. Like when you have an encoder and a decoder, you need to send in, let's say, the English version of a sentence and the French version of a sentence. You need to have corresponding text. With decoder only, you just have to send in text. So you may have heard of GPTs referred to as sort of autocomplete on steroids. This is kind of what it's doing. You're feeding in large corpuses of text. You're training it to learn what the most likely next token is given this context. And you don't have to like pair that up to create a training set. You just throw large amounts of text at it. And the way that you use that when you're auto-regressing, when you're inferring, is your prompt just goes into the decoder, just SOS, then your entire prompt. And that goes straight into the decoder, and then it's just predicting tokens that would come after your prompt. And that's how you use a decoder-only transformer. And that's what, GPT-4 is, that's what Claude is. I'm sure there's a lot of other changes they've made, but they're decoder only. And that brings us to the conclusion. So hopefully this all made sense. Hopefully, what I hope you take away is that transformers, they take in tokens. These tokens are embedded in meaning space, and the transformer is learning how to take each one of these vectors that point to a particular point in meaning space that means something, and it's moving them through space, and it's actually changing the meaning space around it, such that out the other end it is moved to the most likely next token. And it does that for every position in your input every single time. It does this using matrix transformations. These transformation matrices really can be thought of as moving these vectors through space. And it's just iteratively moving these vectors to the next position. And that's kind of what that's what allows it to predict the next token. And then that element of randomness, that probability distribution that comes out, is what allows it to sound sort of much more human and feel much more magical, because it's giving you different responses every time. And that's it. So with that, I'm going to turn the camera back on. I'm going to move on to questions. Okay, question number 1. What advancements in training techniques have contributed to the state-of-the-art performance of transformer models in NLP tasks? That's a great question. For me, I think one of the major breakthroughs in the transformer is that masking step. That masking step that sort of, it removes future words from the context of each word, and that's what allows the transformer to train on every position in your input at the same time, right? If you didn't have that, you would have to train it on if you had the input, where does the queen live? You'd have to train it on the SOS input. Then you'd have to train it on SOS ooh. Then you'd have to train it on SOS ooh habit, right? You'd have to go through every one of those permutations. And yeah, so by being able to train it at every position at once, particularly as your inputs get longer, I think that's one of the major breakthroughs in that the transformer made. Okay, next question. What challenges remain in further refining transformer architectures, particularly in handling ambiguity and context in natural language? That's a tough one. I think that the attention mechanism has gone a long way in helping to handle context, and the fact that you can apply them iteratively, I think is one of the things that makes the transformer special. It's why the paper is called "Attention is All You Need." I think there have been advances in the way attention is applied. So I think there is a lot of room for improvement, which is why this field is moving so quickly. But I think it's really that attention mechanism that is correlating each word in the input with every other word in the input, and assigning sort of importance, how much context each word gives to every other word, that helps them solve the context problem. So I can't, I don't think I can answer, how they're, where the next breakthrough is going to come from. But I think it's the attention mechanism that handles the ambiguity in the context, largely in the existing models. Next question. How can the knowledge gained from understanding transformer models be applied to other domains within AI and machine learning? This, I think, is a really interesting question. So it is predicting the next token, and it's really predicting the next vector. So if you had sequential data that wasn't necessarily words, but it was sequential data that you believed had some sort of underlying set of rules. If you could take that data and create an embedding for it, and then feed that embedding through a transformer, I don't see why that transformer couldn't predict the next vector. And then you have to figure out how to turn that vector back into whatever it is that your embedding model was running on. But I don't personally see any reason why you couldn't apply the transformer to any sort of sequential data that you could create an embedding model for, as long as it had some set of rules that it could model. I think that would work. So yeah, I think there's a lot of stuff that can be done there. And then I think we have one question here. One question left. Is decoder only analogous to masked attention computationally? They're definitely linked, right? So your decoder only is going to use masked attention for sure. I think where I struggle a little bit is you're not going to have cross attention block in your decoder only, because you're not going to have an encoder to give to provide decay in the V, right? It's going to be decoder only, so your attention can only be self-attention, but you're still going to need to mask it because during training, as you're feeding in these sequences, you still want to train every position. So you're still going to need to mask. So they're definitely linked. You definitely need the masked attention step in a decoder only scenario. You're not going to have the cross attention step, so they're definitely linked. I don't know if analogous is the word that I would use to describe that linkage, but they're definitely linked. So good question. And I believe that brings us to the end of the question. I do want to point out there are some resources under the Handouts tab, including a Jupyter notebook that allows you to generate some of those animations from early on. And thank you for participating. If you have a moment, please fill in the survey. If you still have a question, you can send it now, and I will try to answer them after we finish. And then I do want to point out that our next event is on September 10th, which is a Tuesday. Looks like it's an hour earlier, 8 a.m. Pacific time, and that is with Certus. I encourage you to join us for that.